Power functions. Number 1, a is equal to n, where n is a positive integer. The graphs of f of x, which is equal to x to the n, for when n is equal to 1, 2, 3, 4, and 5, are shown in figure 11. These are polynomials with only one term. We already know the shape of the graphs of y equals x, a line through the origin with slope 1, and y equals x squared, a parabola. So here we have y equals x, which is a line. Y equals x squared is a parabola. Here is your cubic function. Here is x to the fourth, and here is x to the fifth. Now, the general shape of a graph of f of x equals x to the n depends on whether n is even or odd. If n is even, then f of x is equal to x to the n is an even function, and its graph is similar to the parabola of y is equal to x squared. Now, if n is odd, then f of x is equal to x to the n is an odd function, and its graph is similar to that of y equals x cubed. Now, notice from figure 12, however, that as n increases, the graph of y equals x to the n becomes flatter near 0 and steeper when the absolute value of x is greater than or equal to 1. So if x is small, then x squared is smaller, x cubed is even smaller, x to the fourth is smaller still, and so on. Number 2, where a is equal to 1 over n, where n is a positive integer. So the function f of x, which is equal to x to the 1 over n power, is equal to the nth root of x, is a root function. For when n is equal to 2, it is the square root function f of x, which is equal to the square root of x, whose domain is including 0 all the way to infinity, and whose graph is the upper half of the parabola y x equals y squared, which is in the first graph here. Now, for other even values of n, the graph of y is equal to the nth root of x is similar to that of y equals the square root of x. Now, for when n is equal to 3, we have the cube root function f of x, which is equal to the cube root of x, whose domain is all real numbers. And recall that every real number has a cube root, and whose graph is shown in figure 13b here. The graph of y is equal to the nth root of x for n odd when n is greater than 3 is similar to that of the cube root of x. Now, the third one is when x is equal to negative 1. The graph of the reciprocal function f of x is equal to x to the negative 1 is equal to 1 over x is shown in figure 14. So here is y is equal to 1 over x. This is the graph here. Its graph has the equation y is equal to 1 over x, or x times y is equal to 1, and it is a hyperbola with the coordinate axes as its asymptotes. This function arises in physics and chemistry in connection with Boyle's law, which says that when the temperature is constant, the volume V of a gas is inversely proportional to the pressure P. V is equal to C over P, where C is a constant. Now, some of these formulas you'll see later on in the course. Now, thus, the graph of V as a function of P, see figure 15, has the general shape as the right half of figure 14. This would be a volume as a function of pressure at constant temperature. Rational functions. A rational function f is a ratio of two polynomials, where p and q are polynomials. The domain consists of all values of x such that q of x does not equal 0. A simple example of a rational function is a function f of x, which is equal to 1 over x, whose domain is where x such that x does not equal 0. This is the reciprocal function graphed in figure 14. Now, the function f of x, which is equal to 2x to the fourth minus x squared plus 1 over x squared minus 4, is a rational function with domain x such that x does not equal plus or minus 2, which is shown in figure 16 here. So the x equals negative 2 and positive 2, and the denominator create those vertical asymptotes. Now, a function f is called an algebra function if it can be constructed using algebraic operations, such as addition, subtraction, multiplication, division, and taking roots, starting with polynomials. Any rational function is automatically an algebraic function. Here are two more examples. f of x, which is equal to the square root of x squared plus 1. And here's the other one, g of x, which is equal to x to the fourth minus 16x squared divided by x plus the square root of x plus x minus 2 times the cube root of x plus 1. When we sketch algebraic functions in Chapter 4, we will see that their graphs can assume a variety of shapes. Figure 17 illustrates some of the possibilities. Here is the graph of x times the square root of x plus 3. Here's the graph of the fourth root of x squared minus 25. And here's the graph of x to the 2/3 times x minus 2 squared. An example of an algebraic function occurs in the theory of relativity, the mass of a particle of the velocity. We will see this formula later on in the book, where m subscript 0 is the rest mass of the particle, and c is equal to 3.0 times 10 to the 5th kilometers per second is the speed of light in vacuum. Trigonometric functions. Trigonometry and the trigonometric functions are reviewed in reference page 2 and also in the appendix C. In calculus, the convention is that radian measure is always used except when otherwise indicated. For example, when we use the function f of x is equal to sine of x, it is understood that sine of x means the sine of the angle whose radian measure is x. Thus, the graphs of the sine and cosine functions are shown in figure 18. Notice that for both the sine and cosine functions, the domain is negative infinity to positive infinity, and the range is the closed interval, negative 1 to 1. Thus, for all values of x, we have the sine of x is in between negative 1 and 1 inclusive, and the cosine of x is also in between negative 1 and 1 inclusive. Now, in terms of absolute value, the absolute value of sine of x is less than or equal to 1, and the absolute value of cosine of x is less than or equal to 1. Also, the zeros of the sine function occur at the integer multiples of pi. That is, the sine of x is equal to 0 when x is equal to n times pi when n an integer. An important property of the sine and cosine functions is that they are periodic functions and have the period 2 pi. This means that for all values of x, the sine of x plus 2 pi is equal to sine of x, and the cosine of x plus 2 pi is equal to cosine of x. The periodic nature of these functions makes them suitable for modeling repetitive phenomena such as tides, vibrating springs, and sound waves. So for instance, when we get to example 4 in section 1.3, we will see that a reasonable model for the number of hours of daylight in Philadelphia t days after January 1st is given by the following function. Now the tangent function is related to the sine and cosine functions by the equation. Tangent of x is equal to the sine of x over the cosine of x, and its graph is shown over here on the right. It is undefined whenever the cosine of x is equal to 0. That is, when x is equal to plus or minus pi over 2, plus or minus 3 pi over 2. And its range is negative infinity to positive infinity. And notice that the tangent function has a period pi. So tangent x plus pi is equal to the tangent x for all x. The remaining three trigonometric functions, cosecant, secant, and cotangent, are the reciprocals of the sine, cosine, and tangent functions, and their graphs are shown in Appendix C. Exponential functions. The exponential functions are functions of the form f of x is equal to a to the power of x, where the base a is the positive constant. The graphs of y is equal to 2 to the x power and y is equal to 0.5 to the power of x are shown in figure 20. In both cases, the domain goes from negative infinity to positive infinity, and the range is going from 0 to infinity. Exponential functions will be studied in detail in section 1.5, and we will see that they are useful for modeling many natural phenomena, such as population growth if a is greater than 1 and radioactive decay if a is less than 1. Logarithmic functions. The logarithmic functions f of x is equal to the log of base ax, where the base a is a positive constant, are the inverse functions of the exponential functions. They will be studied more in section 1.6. Figure 21 we can see shows the graph of 4 logarithmic functions with various bases. In each case, the domain goes from 0 to positive infinity, and the range is going from negative infinity to positive infinity, and the function increases slowly when x is greater than 1.